Right, so last time we were looking at a function from, say, R, or it could be some interval in R. And then we say that, and then we have a point x in R. And we say that f is differentiable at x0 if, when we form this different quotient, so this was this quotient here, if this thing here has a limit as if this here has a limit as x goes to x0. Right, and so again, this means that there is some number so that if x is sufficiently close, is delta close to x0, then this quotient here is close to that number, right? And it's always assumed that x is not equal to, right? So that the denominator makes sense. So that is what it means for a function to be differentiable. And then one of the first things we saw was that we had a lemma that if f is differentiable at x0, then it implies that it's also continuous at x0. Right. And then we had four, just very briefly, we had four rules that if you had two functions, f and g, and they're both differentiable, and you're looking at where you add the two functions, then the sum here of the two functions is also differentiable, and the derivative is the sum of the derivative. Another thing we had was that if you take a constant times a function, and this function is differentiable, then this new function is also differentiable, and the derivative is that constant times the derivative of the original function. And then the third thing was the Leibniz rule. And that was if you have these two functions, they're differentiable, and you take the product and you take the derivative that exists and is equal to the derivative of the first times the second plus the first times the derivative of the second. And then the fourth of these was the quotient rule. And the quotient rule was that you have again these two functions. You assume that g here is not equal to 0 at any point. And then you're looking at the quotient here. And the quotient is also differentiable. And the derivative is given by this formula. This is the formula for the derivative, where this is the function multiplied by itself. Right? And then there was a last rule that was the chain rule. So the chain rule and that was that if you take a function, say from some interval into some set, let's call it, let's say that the interval that the function is defined is some interval from a to b, and this function takes value in another interval from c to d, and then you have a function g that is defined on c to d into R. Then you can look at the composition, right? You take some x, and you first apply f to it, and then afterwards you apply g. And this is typically written as this. And the chain rule was that if f and g are differentiable, then this the composition here is also differentiable, and the derivative of the composition is the derivative of the second function evaluated at this point here times the derivative of the first in x. So this was the chain rule. Okay, that was just a quick recap. And now the first thing we'll be interested in is if we have, so suppose that f here is a function, let's say defined on some interval from a to b into r, and f is differentiable. It doesn't need to be differentiable for this here to make sense, but we say that x0 and x0 is now in the open interval here. We say that, so we say that x0 is, so we say that f has a local maximum, at x0 if there exists delta greater than 0, such that if you restrict f and you just think about f on this little interval around x0, so you're forgetting about how f looks like everywhere else, then if you're looking at the maximum of this function, so this means that, so this is the same as just the maximum of f on this little interval, then the maximum is achieved at x0. Right? If this is the case, so you have the picture here, you have a function, we talked about this a little bit last time, you have a function, maybe the function looks like this, and this here point here is x0, and so this here is the value at x0, and you see that there's some little interval, say this interval here. If you're looking at the function in this little interval, then it's clear that the maximum is at x0, right? But of course, it's just a local maximum. If you were allowed to move further away over here, you see that the value of the function is much larger, right? So this is a local maximum, and for this to make sense, you don't need the function to be differentiable. But we will, when we apply it, we will assume that it is differentiable. So this is a local maximum, right? And this is sort of the picture, right? That is, it's just a maximum near, if you're looking at values near x0, but it's not a global maximum. Of course, it could be a global maximum. And then similarly, for a local minimum. And I'll just draw a picture, because the definition is kind of obvious. It's the same, right? That you take a function here, and you're looking at, and so the function maybe could look like this. Right? And you see that if this here was x0, then in some little neighborhood around x0, the value here would indeed be the minimum, right? But if you're moving much further away, then there might be other points that are even smaller, where the value is even smaller, right? So this is like a local minimum. And so the first observation you have about this is the following lemma. If f here is a function, say on an interval like this, is differentiable, and has a local maximum or minimum, local minimum at x0. And now here, if I'm thinking about a function defined on a closed interval like this, it's important that where the local max or min is in an interior point. It's not allowed to be one of the boundary points. So if it has a local, if it is differentiable and it has a local maximum or minimum at such an interior point, then the claim is that then the derivative at x0 is equal to 0. Okay? And so now let's try to prove that. So we have here, right, so the picture is, let's just assume, so assume that f has a local maximum at x0. If it's a local minimum, the argument is the same with obvious modifications. Okay, so you have some picture like this. Again, here you have x0, and now this here is like the function that, oops, maybe this. So this is like the function. Right? We see that at the value here at x0, it's maximum. And then who cares? You know, we don't care about what happened when you are further away here, right? And so you divide into two cases. You're looking at where x here is bigger than x0. If x is bigger than x0, and now you're looking at, so then you have that f of x minus f of x0, right? The value here is maximum, so this value here is, right, so if this is the case and x is sufficiently close to x0, right? If it's very close here, then it has a maximum at this point. So this means that this difference here is non-positive, right? This didn't really use that it was strictly bigger than, right? It just used that it was close to x0, right? But now this is where we're using that it's bigger than, because we also have that x minus x0, and again, this is where this assumption is used. This thing here is positive, right? So this means that if you take something non-positive and you divide it by something positive, then what you get is something that is non-positive, right? So this means that, so this implies that for the difference quotient, f of x minus f of x0, x minus x0, right? Again, this here is non-positive, this here is positive. This means that the whole thing is non-positive, right? So as you are approaching, as you're going towards x0 from the right, the difference quotient here is non-positive, right? If you now go to x0 from the left, if you go in this direction, so this means that now you have x here is less than x0, right? And sufficiently close. So if you have that, then, well, you again have, this was just because it was a local maximal, you still have that this thing here is non-positive. But now you have that, now we have that x minus x0, right? This thing here now is, right, because of this. This means that this thing here is strictly less than 0, right? So you take something that is non-positive and you divide it by something negative, then you get something non-negative, right? So therefore, this implies that for the difference quotient, f of x minus f of x0, for the difference quotient here, you get that this thing here, this is non-positive, this is negative. This means that this here is non-negative, right? So as you're coming in, so you see that as you're approaching in this direction to x0, then the difference quotient is non-positive. When you're coming in here, it's non-negative. But it has a limit. And so the limit from this side would have to be, right, this is the limit from this side would have to be non-positive, and the limit from this one non-negative, so therefore the limit must be 0, right? So we conclude that the limit here, hence, the limit here, as x goes to x0, of f of x, of the difference quotient, must be 0. And so this is the derivative at that point. Right? And similarly, if it was a local minimum, okay? Now, and a point where the derivative, so maybe I'll just say that. So if f prime at x0 is equal to 0, then we often say that then x0 is said to be a critical point. For f, okay? And let me just give you an example. So, I mean, let's give you two examples. So suppose you take f of x equal to x squared, right? This here is a polynomial. We know how to compute the derivative of any polynomial. This is just using the Leibniz rule. And I mean, using these rules, in this case, you would only need the Leibniz rule together with, we knew what the derivative of the function f of x equal to x is. So in this case, the derivative of this here is 2x. And so this means that x equal to 0 is a critical point. It's actually the only critical point. And so you see in this case, this is how the function looked like. Right? This is sort of how the function looked like. Here you have 0. Right? Another example is that if you take another polynomial where it's instead of x to the power 2, it's x to the power 3, then the derivative of this function is 3x squared. Right? And so you see again that x equal to 0 is a critical point. The derivative here, if you plug in 0, gets 0. So this here is a critical point. But in this case, the graph of the function for this example here, the graph looks like something like this. It becomes very flat here, like this. Okay, and so you see that 0 is a critical point, but it's not like it has a local maximum or minimum. Okay, and it's this, yeah. Okay, so the next thing I want to do is I want to now apply it. I want to apply this simple observation, and I want to apply it to get a consequence, a simple consequence, and then I want to apply that simple consequence to get a lot of other consequences. So the first thing I want to do is what's called Roller's lemma or Roller's theorem. So we have so this is the following. That I have a function f from a to b into r, and I'm assuming that f is differentiable. And I'm also assuming that the value initially and the value at the end, that those two values are the same. Sometimes one said those values equal to 0, but it's just they just need to be the same. And then the claim is that then there exists x0, where x0 is strictly between a and b, and the derivative at this x0 is equal to 0. Okay? And so the idea is just very simple, that you have a function, and the function initially, this is at a, here you have b. The function initially and at the end up at the same value. So this here is, right, so this here is f of a, and that's the same as f of b. And then who knows what happened in between? Maybe like this. And the claim is that then there's always some point where the derivative is 0. In this case, it looks like that those two would be the point, right, where the derivative was 0. And the proof is just this. So prove that there's 3 cases to consider. One is, I mean, you don't really have to divide it up by this, but let me divide it up into these 3 cases. One is that the function here is constant. It's everywhere equal to the same. Right? But if the function is constant, then the derivative is 0. Right? We have already proven that. Case 2, there exists somewhere there exists x such that the value at this x is strictly bigger than the value at the endpoints. And then case 3, there exists an x such that the value at this x is strictly less than the values at the endpoint. Right? It's clear that one of these 3 cases happen. Right? I mean, of course, it could be that case 2 and 3 could both happen. Right? But at least one of the 3 cases would happen. Right? In case 1, we already know that the derivative is 0 everywhere. So let's just look at case 2. Case 3 is similar. Right? So if there exists some x where the value, so in this picture here, this here is maybe x, the value here is larger than at the 2 endpoints. Right? Well, by the extreme value theorem, right, that we proved earlier, just because if a function is differentiable, it's also continuous, by the extreme value theorem, there exists somewhere where actually the maximum is achieved. Right? And since somewhere in between, in this case here, the maximum is not achieved at the two endpoints, right? So the maximum must be achieved at an interior point, right? But now it's not just a local maximum, it actually is a maximum, but already if it was a local maximum, the derivative would be 0 at that point, right? So this proved case 2, and case 3 is similar, right? So this is Rayleigh's theorem. Okay, now Rayleigh's theorem have then a bunch of applications. And the first one is to what's called the mean value theorem. And there are two versions of the mean value theorem. One is the actual mean value theorem, and the other is like a fancy version of it, where you have two functions in play at the same time. And that's called the Cauchy mean value theorem. So consequence, for first consequence, of Rayleigh's theorem and this is the mean value theorem. Okay, and so the first one is the actual mean value theorem. And the actual mean value theorem say that if you take a function f from a to b on some interval like this, and the function is differentiable, then there exists a x strictly, there exists x, where x is strictly between a and b, and so that the derivative at x is equal to the difference quotient, where you do the difference quotient at the two endpoints. So this here is this side of it. That's what you often call the mean, and the mean is equal to the derivative at some intermediate point. This is what they say. Okay. And so now, right, so this seems a lot better than Rayleigh's theorem, but it's an easy consequence of Rayleigh's theorem. Because if you look at, so if you look at, suppose you take the function, so prove, suppose you take the function h of x equal to f of x minus f of b minus f of a divided by divided by b minus a times x minus a. Suppose you're looking at this function here, h, right? Then observe first that this function is differentiable. This is just a constant, right? This is just a linear function, right? This is a is a constant also. So this is differentiable. This is a constant. This is differentiable, and we're subtracting it from a differentiable function. So h is differentiable. H of a is f of a, right? And then this thing here minus f of b minus f of a, b minus a, and then this here is a minus a. So this is 0, so this is f of a. H of b is f of b minus, and then f of b minus f of a, b minus a, and here you plug in b, so b minus a. And so you see that these here cancel out, and you are right? So you are subtracting this, but this is a minus minus, so you're adding. So this is f of a, right? So you see that for this function, it's the value at a and b are the same, right? So now we apply Wallis theorem.